Hi, Chem Peeps. We are going to determine oxidation numbers of elements found inside polyatomic ions today. This is done a little bit different than cross-up, which we do with neutral compounds. Because polyatomic ions have an overall charge, we have to do it a little bit differently. So with this first example of sulfate, I'm going to make a T-chart. In other words, I'm dividing it. I'm going to make this side the positive side, this side the negative, nope, not -1, but just negative. And then we're going to make it balance out to equal -2. Just like in cross-up, we always look up the one on the right because it's the most electronegative and it will dictate the other elements' charge in the polyatomic ion. So oxygen is in family 16 and it is a -2. So one oxygen would have a charge of -2, but we have 4 of them. So we're going to take it times 4 and get a -8. So on the negative side, we have a -8. What does the positive side have to be? In other words, what positive plus the -8 is going to equal -2? And that is going to be a 6. So sulfur's charge is +6. So in this problem, sulfur is +6, which we would not have predicted from our chart because sulfur is also in the same family as oxygen. But because oxygen is a more electronegative atom, it takes the trend of -2 and forces sulfur as a +6. Okay, let's look at our next example, which is the oxalate ion here. We have carbon with a 2 and oxygen with a 4. Let's make our T-chart. The positives on this side, negatives on this, and they're going to balance out to equal -2. Look the one up on the right. Oxygen, we have seen in our examples, is usually a -2. Times 4 is -8. So we have what? Plus -8 equals -2. And again, it's 6, but it's a little bit different because look, there are how many carbons in this compound? There are 2. So we've got to divide this by 2, and the overall charge on carbon is a +3. So in this problem, one carbon is a +3, and one oxygen is a -2. I threw in the next example because it's kind of an oddball. Most of the polyatomic ions, when you look in the chart, are of a negative nature, but ammonium is a positive polyatomic ion, and it doesn't normally fit the T-chart example. So for example, over here, when we did this one, the plus side was here and the negative was here. Ammonium, it has a hydrogen, and hydrogen is in family 1. And it has a +1 charge, but it's found on the right side where the anions belong. So it's an oddball in many regards. So we're going to just assign that +1 charge here. Okay, we're still going to have a T-chart, but this time the positive is going to be on this side, the negative's over here. And we don't have just one hydrogen, we have 4. So 4 times 1 is a +4. Remember, this has to balance out to equal a +1. So what plus the +4 equals a +1, and that will be a -3. So nitrogen's side is a -3. So we have nitrogen equals -3, and one hydrogen is a +1. Okay, our final example is phosphate. And we have phosphorus and oxygen. We're going to make that T-chart. Positive on this side, negative on this side, and it must balance out to equal -3. Look the one up on the right, and it's oxygen. Oxygen is a very common anion in compounds. So one oxygen, we know from family 16 that oxygen is going to be a -2, but we have 4 of them. So 4 times -2 is -8. So what? Plus the -8 equals a -3. Well, that's going to be 5. So in this example, phosphorus is a +5 and one oxygen is a -2. And learning how to do this will be very useful when we get to redox reactions and how to balance them. Find more information on my YouTube at Kim's Chem Chats, and I will check you later.